In the vast, silent theater of space, where galaxies dance across eons and stars burn with the fury of creation, something extraordinary has captured our attention. Something that challenges our understanding of cosmic law. Something that whispers of possibilities we've only dared to imagine in our wildest dreams. 3IA. Atlas survived its perilous journey around our lunar feet. That should have been predictable, calculable, ordinary. But when astronomers recalculated its path using fresh data, the numbers refused to align. The object wasn't where gravity's mathematical certainty said it should be. Its orbit had shifted subtly, undeniably, impossibly. A small but measurable acceleration in the vacuum of space. That's not supposed to happen. Not according to the laws we've spent centuries documenting. Not according to the physics that govern our universe. Then came the confirmation that sent ripples through the scientific community. The team at the Galileo Project, led by the brilliant but controversial Avi Loeb, reviewed the trajectory data and found something extraordinary. A statistically significant non-gravitational component identical to what was observed in Oumuamua back in 2017. The question became impossible to ignore. Is this a natural comet behaving in ways we've never witnessed before? Or is it something else, something deliberately adjusting its course through our solar system? NASA's official silence only deepened the mystery, creating a void where speculation flourished. This isn't just another interstellar rock drifting through our cosmic neighborhood. This is the first confirmed case of an object accelerating after perihelion, after its closest approach to our sun. By the end of this journey, you'll understand why some astronomers are quietly calling 3IA Atlas the most important object ever detected by humanity. Stay with me as we unravel this cosmic enigma, piece by mysterious piece. Chapter 1. The reappearance on October 29, 2025. 3IA Atlas reached perihelion, the moment when an object comes closest to our sun, that brilliant star that has watched over Earth for billions of years. For 3IA Atlas, that distance was about 1.4 astronomical units, or roughly 210 million kilometers, close enough to feel the sun's intense heat, far enough to remain a cosmic mystery. It was a critical moment, for perihelion is when comets are most alive, most active. The sun's relentless heat causes ice on the surface to sublimate directly into gas, blasting material into space like cosmic fireworks. This creates a coma, ghostly cloud of gas and dust around the nucleus. It creates a tail pushed away from the sun by radiation and solar wind, a celestial banner announcing its presence. But there was a problem. From Earth's perspective, 3IA Atlas was directly behind the sun, hidden in the blinding glare of our star. Ground-based telescopes were blind, unable to penetrate the intense light. For nearly 6 weeks, the object disappeared from view, vanishing like a ghost in daylight. During that time, we had to rely on our mechanical eyes in Space NASA's SOHO Observatory, ESAS, Solar Orbiter, the stereo probes. These instruments, positioned away from Earth's shadow, could still track the comet as it swung past the sun. And they saw something strange. Between October 21st and October 29th, 3IA Atlas brightened rapidly, much faster than any model predicted. The increase in luminosity was about 5 times greater than what calculations suggested for a comet. At that distance, this wasn't normal. Comets brighten as they approach the sun, yes, but this surge was extreme, almost violent. The color of the light was odd, too newsily blue, like a flame burning at an impossible temperature. Most comets appear reddish because of dust reflecting sunlight, but 3IA Atlas was emitting a blue glow, suggesting intense gas activity. A chemical signature that didn't match our expectations. Some researchers attributed this to carbon dioxide. Earlier observations had shown that 3I Atlas was rich in CO2 ice, which sublimates at lower temperatures than water ice. Perhaps the sun's heat was triggering a massive release of gas, a cosmic exhalation we hadn't anticipated, but others weren't so sure. When the data was analyzed more closely, something else became apparent. The brightening wasn't symmetric. It was concentrated on one side of the object, the side facing the sun. Now this is where things get interesting, where the ordinary transforms into the extraordinary, where our understanding begins to fray at the edges. Chapter 2. The Oberth Windowlets. Talk about a concept that sounds like science fiction but is very real: the Oberth effect. In orbital mechanics, the Oberth effect describes how a spacecraft can maximize its change in velocity by firing its engines at the point of closest approach to a massive body. When you're moving fast through a strong gravitational field, even a small thrust produces a large change in kinetic energy. It's a principle used by space agencies all the time. When a probe approaches Jupiter, for example, it can use a brief engine burn at perihelion to slingshot itself toward another destination with minimal fuel. A cosmic cheat code, bending the rules of travel through space. But the Oberth effect works in reverse too. If you want to slow down, the most efficient time to fire a braking thrust is also at perihelion. You're moving fast. The gravitational pull is strong. A small burn can drastically reduce your velocity, allowing you to enter a bound orbit instead of shooting back out into interstellar space. This is called a reverse Oberth maneuver. And here's the thing for 3EA Atlas. Perihelion occurred on October 29th. It was traveling at 68 kilometers per second at that moment, hidden from Earth's view by the blinding light of our sun, which means if something wanted to perform a clandestine course correction, that would have been the perfect time to do it. The cosmic equivalent of changing lanes in a blind spot where no one can see you. Now, to be clear, no one is saying that's what happened. The scientific community is divided, debates raging in observatories and universities across the planet. But the timing is notable because when 3I Atlas re-emerged in early December, its trajectory had changed. Let's look at the data. Let's follow the numbers where they lead us, even if the destination is uncomfortable. Chapter 3. The trajectory deviation tracking the path of an interstellar object is complex, like trying to follow a single snowflake in a blizzard across continents. You need precise measurements from multiple observatories over an extended period. Small errors in position or velocity can compound over time, leading to incorrect predictions, false trails in the cosmic snow. But by early December 2025, astronomers had accumulated enough data to recalculate 3-Aya Atlas's orbit with high confidence. And that's when the anomaly became clear, undeniable, impossible to ignore. The object's trajectory had shifted, not dramatically, but measurably. According to models, 3-Aya Atlas should have been traveling on a purely hyperbolic path on orbit not bound to our sun, a cosmic visitor passing through, never to return. It came from interstellar space. It swung past the sun. It should be heading back out again into the infinite darkness between stars. But the updated orbital elements showed something different. The eccentricity of the orbit had decreased. Eccentricity is a measure of how elongated an orbit is. A value of 1 means the orbit is parabolocrete on the edge of being bound. A value greater than 1 means hyperbolic and bound, free. And a value less than 1 means elliptical bound, captured. Before perihelion, 3-Aya Atlas had an eccentricity of about 1.0016, hyperbolic but just barely. After perihelion, the eccentricity was measured at 0.9999987. That's a difference of 0.29, tiny, but significant because it means the object is now on a bound orbit. It's not leaving the solar system, at least not anytime soon. It's been captured like a cosmic moth drawn to a flame it cannot escape. Now, there are natural explanations for this. Comets can lose mass through outgassing, and the recoil from that gas can alter their trajectory. This is called a non-gravitational force, and it's been observed in many comets. But here's the problem. The amount of mass 3-Aya Atlas would need to lose to produce this change is enormous. We're talking about millions of tons of material ejected in a very specific direction. And the observations don't support that. The comet didn't show signs of a massive outburst. There was no sudden increase in coma size, no dramatic tail formation, just the concentrated brightening on the sunward side. So what caused the trajectory change? That's the question Harvard astrophysicist Avi Loeb is asking. That's the question that keeps astronomers up at night, staring at computer screens, recalculating, wondering if they're witnessing something extraordinary. Chapter 4. Loeb's Hypothesis. Avi Loeb is no stranger to controversy. In 2017, he suggested that the first interstellar object, Oumuamua, might have been an alien spacecraft. The idea was based on Oumuamua's unusual acceleration, which couldn't be fully explained by outgassing. Most scientists disagreed. They argued that Oumuamua was probably a comet and that the acceleration was due to the sublimation of hydrogen ice, which is difficult to detect, but Loeb wasn't convinced. And now, with 3-Aya Atlas, he's making a similar argument, standing against the tide of conventional thinking once again. On December 14, 2025, Loeb published a paper on the Arxiv preprint server. The title was Direct Evidence for Non-Gravitational Acceleration in Interstellar Object 3-Aya Atlas. In the paper, Loeb and his colleagues present an analysis of the trajectory deviation. They calculate the force required to produce the observed change in orbit, and they conclude that natural outgassing cannot fully account for it. The numbers don't add up according to their models. The recoil force from sublimating gas would need to be about 10 times stronger than what's observed in typical comets, and it would need to be directed almost perfectly in the right direction to produce the orbital change. That's possible, but unlikely, like throwing a dart at a bullseye a mile away in a hurricane. So Loeb proposes an alternative. What if the acceleration wasn't caused by outgassing? What if it was caused by something else, something more deliberate? He stops short of saying alien spacecraft, but he doesn't rule it out either. Instead, he suggests that 3-Aya Atlas could be a technological artifactor probe, a relic, something built by an intelligence that existed long before our solar system formed. It's a bold claim, and it's met with skepticism from the broader scientific community. But the data is real, the acceleration is real, and the questions it raises are real too. So let's examine the evidence more closely. Let's follow the trail of breadcrumbs wherever it leads, even if the destination challenges everything we thought we knew. Chapter 5. The acceleration vector when an object accelerates. It doesn't just change speed, it changes direction too. And the direction of that acceleration tells us something about the force causing it, like reading the footprints of an invisible giant. For 3-Ia Atlas, the acceleration vector points almost directly away from the Sun. This is consistent with the solar radiation pressure effect, where photons from the Sun push on the object's surface. But the magnitude of the acceleration is too large for radiation pressure alone. Loeb's team calculated that the acceleration is about 5.9 times 10 to 5 astronomical units per day squared. In simpler terms, that's about 0.014 meters per second squared, normalized at 1 astronomical unit from the Sun. To put that in perspective, that's about 1/1700th the strength of Earth's gravity. Tiny but measurable, significant. And here's where it gets interesting. If you extrapolate that acceleration forward, the trajectory of 3-Aya Atlas changes significantly. Instead of shooting back out into interstellar space, the object would curve inward toward the inner solar systems, specifically toward a region where it could potentially intercept Jupiter. Now, this doesn't mean 3-Ia Atlas is heading for Jupiter. The data is still preliminary. Orbital calculations are complex, and small errors can lead to large uncertainties over time. But the possibility is there, and it raises an uncomfortable question. If 3-Aya Atlas is accelerating in a way that could bring it closer to the gas giant, is that intentional? Or is it just a coincidence, a cosmic accident with profound implications? Let's look at what makes Jupiter so interesting. Let's explore why this giant planet might be a destination worth traveling toward, even across the vast emptiness between stars. Chapter 6. The Jupiter connection. Jupiter is the largest planet in our solar system. A majestic giant with a mass more than twice that of all the other planets combined. It sits at a critical position about 5.2 astronomical units from the Sun, a gravitational anchor in the cosmic sea. For any spacecraft or probe entering the inner solar system, Jupiter is valuable. You can use it to slingshot yourself toward other destinations, or you can use it to slow down and enter a stable orbit. It's a cosmic highway interchange, a gateway to the outer solar system. And then there are the moons. Jupiter has 95 known moons, but 4 of them are large enough to be truly interesting worlds in their own right. Ganymede is the largest moon in the solar system, bigger than Mercury. It has a magnetic field which is rare for a moon, and it likely has a subsurface ocean beneath its icy crust, a hidden sea warmed by tidal forces. Europa is famous for its global ocean. Beneath a layer of ice, there's more liquid water than all of Earth's oceans combined. And where there's water, there's the potential for life, a possibility that tantalizes scientists and dreamers alike. Callisto is old, ancient. Its surface is heavily cratered, untouched by geological activity. For billions of years, it's a time capsule, a window into the early solar system. Io is volcanic, the most geologically active body in the solar system, constantly resurfaced by eruptions of sulfur and silicate rock, a world being born and destroyed simultaneously. 4. A probe or a spacecraft or any kind of technological artifact, the Jovian system is a goldmine. Resources, energy, stable orbits, and low gravity, which makes launching and landing easier. If something wanted to establish a foothold in the solar system, Jupiter would be a logical choice. Now, there's no evidence that 3-Ia Atlas is heading for Jupiter with any kind of intent. The trajectory is still uncertain, and most scientists believe the object is a natural comet behaving exactly as comets should. But the possibility is worth considering, because the timing is curious. 3-Ia Atlas will pass within 0.36 astronomical units of Jupiter on March 16, 2026. That's about 54 million kilometers, close enough for detailed observation. And if the object were to perform another course correction at that point, it could enter orbit around the planet. Again, this is speculation, but it's not baseless speculation. It's grounded in orbital mechanics and the observed acceleration. So, let's examine the alternative explanations. Let's explore the natural possibilities before we venture into the extraordinary. Chapter 7. The natural explanation. The simplest explanation for the acceleration is that 3-Ia Atlas is a comet, and the non-gravitational force is caused by outgassing. This is the consensus view among most astronomers, the path of least resistance. The explanation that doesn't require us to rewrite our understanding of the universe. Comets are icy bodies. When they approach the sun, the heat causes the ice to sublimate. The escaping gas creates a recoil force, like a tiny rocket engine. This force can change the comet's orbit. We've seen this many times before. Comet Halley, Comet Ient, even the famous Comet Hale-Bopp. All of them exhibited non-gravitational accelerations due to OUT-GASSING. So why is 3-Ia Atlas any different? Well, there are a few reasons. First, the magnitude of the acceleration. As mentioned earlier, the force required to produce the observed trajectory change is unusually large. It's not impossible for a comet to generate that much thrust, but it's uncommon, like finding a snowflake that weighs as much as a car dot. Second, the direction. The acceleration vector points almost directly away from the sun. For a typical comet, the outgassing is often asymmetric, creating a net force at an angle to the soon object line. But for 3-Ia Atlas, the force seems to be radial. that's unusual. Third, the lack of visible gas. Spectroscopic observations of 3-Aya Atlas have not detected the expected signatures of water vapor or other volatile gases. The coma is there, but it's faint, and the composition doesn't match what we'd expect for a comet undergoing significant outgassing. Of course, this could be a detection issue. Maybe the gas is there, but we're not seeing it because of the object's distance or the sensitivity of our instruments. Maybe the composition is just different from what we're used to. After all, 3-Aya Atlas comes from another star system. Its chemistry could be exotic, alien to our understanding, but the lack of clear evidence for outgassing is puzzling, and it opens the door to other interpretations. One possibility is that the acceleration is caused by a structural change in the object. Maybe 3-Aya Atlas is rotating and the centrifugal force is causing it to shed material in a specific direction. Or maybe there's a large fragment that broke off during perihelion, creating an impulse, like a ship losing a piece of its hull in a storm. Another possibility is that the object has an unusual surface. Maybe it's highly reflective, like a mirror, and the solar radiation pressure is stronger than expected. This was one of the hypotheses for Oumuamua's acceleration. But again, the numbers don't quite add up. The reflectivity would need to be unrealistically high, and the shape would need to be just right to direct the radiation pressure in the observed direction. So we're left with a mystery. A small but measurable acceleration that doesn't fit neatly into our existing models. And that's where the debate begins, where science and speculation dance on the edge of discovery. Chapter 8. The Data. Silence hears something odd. On October 2nd and 3rd, 2025, 3-Aya Atlas made its closest approach to Mars. At that time, it was about 30 million kilometers from the planet, close enough for several Mars orbiters to observe it. NASA's Mars Reconnaissance Orbiter has a camera called Horizon. It's one of the most powerful cameras ever sent to another planet. It can resolve features as small as a meter across on the Martian surface, and it pointed at 3-Aya Atlas. The images should have been incredible. At that distance, Horizon could potentially resolve details on the comet's nucleus. We could see the structure, the rotation, maybe even individual jets erupting from the surface. But those images haven't been released. In early October, there was a US government shutdown. NASA's communications office was furloughed. And while critical mission operations continued, the public release of non-essential data was delayed. By the time the shutdown ended, 3-Aya Atlas had moved on. It was behind the sun, out of view, and the high-res images still unreleased. Now, there are legitimate reasons for this. Data processing takes time. Images need to be calibrated, analyzed, and peer-reviewed before they're made public. NASA has protocols, and those protocols were disrupted by the shutdown. But the delay has fueled speculation. Some people believe NASA is withholding the images because they show something unexpected, something that doesn't fit the natural comet narrative. Avi Loeb has been vocal about this. In a blog post on December 10th, he wrote, "The public deserves to see the data. Science thrives on transparency. If the images show nothing unusual, fine. But the longer we wait, the more questions arise." He's not wrong. Transparency is important, and the silence, intentional or not, creates space for conspiracy theories to grow like weeds in an untended garden. On social media, people are speculating. Some claim the images show structures, patterns, geometries that don't occur naturally. Others suggest the comet changed appearance after perihelion, revealing a metallic core or artificial components. These claims are unsubstantiated. There's no evidence to support them, but the absence of official data leaves a vacuum, and that vacuum gets filled with speculation. It's worth noting that ESA's Mars orbiters did release images. The ExoMars Trace gas orbiter captured 3 EA Atlas on October 3rd. The images show a fuzzy white dot nose structures. No anomalies, just a comet. But those images were taken from a greater distance and with lower resolution than what Horizon could achieve, so the question remains, what did Horizon see? As of today, December 19th, 2025, we still don't know. And in that silence, possibilities multiply like stars in the night sky. Chapter 9. The nickel anomaly. Let's shift focus for a moment. Because there's another piece of the puzzle that's worth examining, a chemical clue that doesn't fit the picture we've painted. In August 2025, astronomers using the Keck to telescope in Hawaii analyzed the light coming from 3IA Atlas. They were looking for spectral signatures, specific wavelengths of light that correspond to different elements and molecules. And they found something unexpected. Nickel, specifically atomic nickel vapor, in the coma of the comet. This was unusual. Nickel has been detected in comets before, but only in trace amounts, and it's usually accompanied by iron, since the two elements often occur together in space. But in 3IA Atlas, the ratio was off. There was a lot of nickel and very little iron. The team calculated that the comet was emitting about 4 grams of nickel per second. That might not sound like much, but over the course of weeks, it adds up to hundreds of kilograms. And the lack of iron was puzzling. In most comets, the nickel-to-iron ratio is close to 1:1. But in 3IA Atlas, it was more like 10:1, or even higher. Why does this matter? Because nickel and iron are typically bound together in meteoritic material. They come from the cores of dead stars, forged in supernova explosions and distributed throughout the galaxy. When a comet forms, it incorporates this material into its icy matrix. So when a comet sublimates, you expect to see both nickel and iron released into the coma. The fact that 3IA Atlas is emitting nickel without iron suggests something unusual about its composition. One hypothesis is that the comet contains nickel carbonyl, a compound where nickel atoms are bonded to carbon monoxide molecules. This compound is highly volatile, vaporizes easily, and could explain the high nickel emission without corresponding iron. But here's the thing. Nickel carbonyl is not a natural compound on Earth. It's used in industrial processes, specifically in the refining of nickel metal. It's toxic, dangerous, and it requires specific conditions to form. In space, those conditions are rare. You'd need carbon monoxide, nickel, and the right temperature and pressure. It's possible, but it's not common. So, the presence of nickel carbonyl in 3IA Atlas is intriguing. It suggests the comet has an unusual chemistry, or it suggests something else entirely. Avi Loeb has pointed to this as another potential sign of artificiality. If 3IA Atlas were a technological object, it might be made of metal alloys, and those alloys could contain high concentrations of nickel. As the object heats up near the sun, the surface could outgas nickel vapor, creating the observed spectral signature. Again, this is speculative, but it's not unreasonable, and it adds to the growing list of anomalies each one, a thread that, when pulled, might unravel the entire tapestry of our understanding. Chapter 10. The antitail here's another oddity. In July and August 2025, when 3IA Atlas was first discovered, astronomers noticed something strange about its appearance. The comet had a tail, but the tail was pointing in the wrong direction. Normally, a comet's tail points away from the sun. This is because the tail is made of gas and dust that's pushed outward by solar radiation and the solar wind. The sun's light and particles create a pressure that drives material away from the nucleus. But 3IA Atlas had a tail pointing toward the sun. This is called an antitail. It's rare, but not unheard of. Antitails occur when larger dust particles are left behind in the comet's orbit. As the comet moves forward, these particles lag, creating a spike of material that appears to point sunward from certain viewing angles. It's usually an optical illusion, a trick of perspective, but for 3IA Atlas, the antitail persisted. It was visible in multiple observations from different telescopes at different locations, and the geometry didn't quite fit the optical illusion explanation. Some researchers suggested that the antitail was caused by a jet of gas erupting from the sunward side of the comet. If the nucleus was rotating and a vent was facing the sun, it could shoot material forward, creating the appearance of a tail pointing toward the sun. That's plausible, but it's unusual. Most comet jets are side vents, not forward-facing. Then, in September, the antitail disappeared. Observations from the Nordic Optical Telescope showed that the tail had flipped. It was now pointing away from the sun as expected. Avi Loeb interpreted this change as significant. In a blog post, he suggested that if 3IA Atlas were a spacecraft, the antitail could have been a braking thruster rocket engine firing to slow the object down as it approached the sun. And when the tail flipped, that could indicate the thrust had been turned off. Mission accomplished. It's a compelling narrative, but it's not the only explanation. The change in tail direction could simply be due to the comet's rotation and the evolving balance between different types of outgassing. Still, the timing is curious. The tail flipped right around the time 3IA Atlas reached perihelion, and that's when the acceleration began. Coincidence? Probably, but it's worth noting another piece of the puzzle that doesn't quite fit. Chapter 11. The Europa Clipper encounter now. Let's talk about something that almost happened. On October 30th, 2025, NASA's Europa Clipper spacecraft was en route to Jupiter. It had launched in October 2024 and was on a long, looping trajectory that would take it past Mars for a gravity assist before heading to the outer solar system. At the same time, 3IA Atlas was passing through that same region of space. Not close enough for a physical encounter, but close enough that the spacecraft might fly through the comet's ion tail. An ion tail is different from a dust tail. It's made of charged particles, ions stripped from the comet's coma by the solar wind. The tail is thin, invisible to the naked eye, but it can extend for millions of kilometers if Europa Clipper flew through it. The spacecraft's instruments could detect those ions, and by analyzing their composition, scientists could learn more about the comet. It was a rare opportunity, a chance encounter with a visitor from another star system, but it didn't happen because of the US government shutdown. Europa Clipper was operating in a reduced capacity. Only essential systems were active. The science instruments were offline. By the time the shutdown ended, the window had passed. Europa Clipper had moved on, and we'd missed our chance. Or had we? There's speculation that the spacecraft did collect data, that its instruments were active despite the shutdown, and that NASA is sitting on the results. Again, this is speculation. There's no evidence to support it, but the idea persists because if Europa Clipper did sample the ion tail, the data could be invaluable. It could tell us about the comet's composition, its volatility, its origin, and if there's anything unusual, anything that doesn't fit the natural comet model, it would be in that data. For now, we wait. We wait for answers that may or may not come, for data that may or may not exist, for clarity in a situation that grows more mysterious with each passing day. Chapter 12. The Fibonacci signal. In late October, a story started circulating online. It claimed the 3IA Atlas was emitting a radio signal specifically, a series of pulses at 1420 megahertz. This is the hydrogen line frequency, the wavelength at which neutral hydrogen emits radiation. And because hydrogen is the most abundant element in the universe, many scientists believe it's a natural frequency for extraterrestrial communication. The story claimed that the signal followed a Fibonacci sequencer, mathematical pattern where each number is the sum of the two preceding ones: 1, 1, 2, 3, 5, 8, 13, and so on. The Fibonacci sequence appears throughout nature, in the spiral of a nautilus shell, in the arrangement of leaves on a stem, in the proportions of the human body. It's a fundamental pattern, one that any intelligent civilization would recognize. If 3IA Atlas were transmitting a signal based on this sequence, it would be a clear sign of intelligence. The story went viral. Social media exploded. People were excited, terrified, curious. Was this it? First contact? But here's the problem. The story was false. No credible observatory has detected a radio signal from 3IA Atlas. The claim originated from an anonymous post on a conspiracy forum and spread because it sounded plausible, because we wanted it to be true. The truth is, radio astronomers have been listening to 3IA Atlas since its discovery. Multiple teams using different telescopes around the world have searched for anomalous emissions, and they found nothing. The object is radio silent. So why bring this up? Because it illustrates how quickly misinformation can spread and how desperately people want answers. The silence from NASA, the missing Horizon images, the unexplained acceleration, these gaps in information create a fertile ground for speculation. And sometimes that speculation crosses the line into fiction. It's important to separate fact from fiction, to rely on data, not rumors, to question but not to assume. 3IA Atlas is real. The acceleration is real. The anomalies are real. But the Fibonacci signal, that's not. That's a reflection of our own hopes and fears projected onto the cosmic canvas. Chapter 13. The Loeb Salin, the grand theater of cosmic discovery, where data meets imagination. Avi Loeb has crafted a new way to measure the extraordinary. He calls it the Loeb scalar classification system that ranks interstellar objects on a spectrum from the mundane to the miraculous, from the natural to the undeniably artificial. This scale ranges from 0 to 10, where 0 represents an object that is definitively natural, with no anomalies, no questions, no mysteries that defy our current understanding of cosmic physics. A score of 10, on the other hand, represents an object that is unquestionably technologically confirmed artifact of extraterrestrial intelligence, the kind of discovery that would rewrite human history overnight. Most interstellar objects we've encountered score low on this scale. Take 2I Borisov, for example. It would score about a 1, a clear, unambiguous comet with a coma, a tail, and spectroscopic signatures that matched our expectations for cometary activity. It was remarkable simply because it was ordinary proof that comets in other star systems behave much like those in our own cosmic neighborhood. Then there was Oumuamua, the first interstellar visitor we detected back in 2017. On the Loeb scale, it might score a 3 or 4. It had unusual features, an elongated shape, an unexplained acceleration, but nothing definitive, nothing that couldn't be explained away with. Enough creative physics, and now we have 3IA Atlas. Loeb gives it a score of 4 to 6, depending on how one interprets the data. Here's his reasoning. The object has multiple anomalies: the trajectory deviation, the acceleration, the nickel emission, the anti-tail, the brightness surge, the alignment with the ecliptic plane. Any one of these could be explained naturally, but together they create a pattern, a profile that doesn't quite fit the standard Comet model. It's like finding a puzzle where each piece looks normal on its own, but when assembled, creates a picture that doesn't match anything we've seen before. Does that mean 3IA Atlas is artificial? Not necessarily, but it means the possibility shouldn't be dismissed out of hand. Loeb argues that science advances by considering all hypotheses, even the unconventional ones. If we rule out the technological explanation purely on philosophical grounds because it makes us uncomfortable, because it sounds like science fiction, we risk missing something extraordinary. He's not saying 3IA Atlas is an alien probe. He's saying we should be open to that possibility and design tests to distinguish between natural and artificial scenarios. One such test is the detection of non-gravitational acceleration. If the acceleration continues, if it's consistent, if it follows a pattern that suggests control rather than randomness, that would be significant. Another test is the Horizon images. If they show structures, symmetries, patterns that don't occur in nature, that would be significant too. But until we have that data, we're left with probabilities, estimates, educated guesses, and that's where we are no suspendere between possibilities, waiting for clarity that may or may not come. Chapter 14. The December 19th OBSR Vieta Riona Day is December 19th, 2025. And today, Bria Atlas reaches its closest point to Earth. The distance is about 1.8 astronomical units, for roughly 270 million kilometers, far, but not impossibly far, close enough that our most powerful telescopes can still capture its light, still analyze its composition, still track its movement with precision. For the next few weeks, the comet will be visible to large telescopes around the world. Observatories are training their instruments on it, collecting photometry, spectroscopy, astrometry, every type of data we can gather from this distance. This is our best chance to understand what's happening. If the acceleration continues, we'll see it in the orbital data. If the comet brightens again, we'll see it in the light curves. If there are new spectral features, we'll see them in the spectra. And if there's nothing unusual, if 3-Aya Atlas behaves exactly as a comet should, then the mystery will resolve itself, and we can move on to the next cosmic puzzle. But here's the thing. The data takes time to process. Observations need to be made, analyzed, peer-reviewed, published. Science isn't instantaneous. It's slow, deliberate, careful. So while the observations are happening now, the results won't be clear for weeks or even months. In the meantime, we're left with what we know so far. 3-Ia Atlas is an interstellar object. It came from outside our solar system. It has unusual characteristics, and it accelerated after perihelion in a way that doesn't fit neatly into our models. Is it a comet? Probably. Is it something else? Maybe. The truth is, we don't know yet. And that uncertainty, that space between what we know and what we suspect, is where discovery happens. Chapter 15. The Jupiter FLY, BY on March 16th, 2026. 3-Ia Atlas will pass within 54 million kilometers of Jupiter. That's the next major milestone in our relationship with this cosmic visitor, and it's another opportunity for observation. NASA's Juno spacecraft is currently orbiting Jupiter. It's been there since 2016, studying the planet's atmosphere, magnetic field, and interior structure. And in March, Juno will turn its instruments toward 3-Ia Atlas. The spacecraft has a suite of cameras and spectrometers. It can measure the comet's brightness, composition, and structure. And because Juno is so close to Jupiter, it will have a better view than any Earth-based telescope. If 3-Ia Atlas performs another course correction during the flyby, Juno will see it. If the object releases material, Juno will see it. If there's anything unusual about the comet's behavior near Jupiter, Juno will see it. This is the moment many scientists are waiting for, because Jupiter's gravity is strong. If 3-Ia Atlas is going to do something unexpected, the Jovian flyby is when it would happen. Of course, there's also the possibility that nothing happens, that 3-Ia Atlas simply swings past Jupiter and continues on its way out of the solar system. If that's the case, it would suggest the acceleration we observed was a one-time event, a fluke. Maybe a large fragment broke off during perihelion, creating an impulse, or maybe there was a brief surge of outgassing that we didn't fully detect. Either way, the Jupiter flyby will give us answers, or at least more data to inform our questions. Chapter 16. The Dark Forest Hypothesis. Let's take a step back and consider a broader question. If 3-Ia Atlas is artificial, what does that mean? Not just for science, but for humanity, for our place in the universe, For our understanding of ourselves, Avi Loeb has referenced a concept called the dark forest hypothesis. It's an idea from science fiction popularized by Chinese author Liu Cixin in his Three-Body Problems series. The hypothesis goes like this. The universe is full of intelligent civilizations, but they're all hiding. Because if you reveal your presence, you become a target. Resources are finite, good space is vast. And if another civilization sees you as a threat, they might decide to eliminate you preemptively. So, the safest strategy is silence. You stay dark. You avoid detection. You survive by remaining invisible. It's a chilling idea, and it's one explanation for the Fermi paradox. The question of why we haven't detected any signs of extraterrestrial intelligence, despite the statistical likelihood that they exist. In this framework, an interstellar probe like 3i Atlas wouldn't announce its presence. It would observe quietly, collect data, and then move on. Or it would stay, establish a foothold. Wait now, this is speculation, pure speculation. The dark forest hypothesis is a thought experiment, not a scientific theory. But it's worth considering because if 3IA Atlas is technological, we need to think about why it's here and what it might do next. Loeb has suggested three possibilities. First, the object could be a derelict probe that was launched millions of years ago by a civilization that no longer exists. It's been drifting through space, inert, following the trajectory it was given long ago. The acceleration we observed could be residual, a final burn of a fuel source that's nearly depleted. Second, it could be an active observer reconnaissance. Probes still functioning, collecting data about our solar system. The acceleration would be intentional, a course correction designed to optimize its observations or extend its mission. Third, it could be something else entirely, something we haven't imagined because our understanding of technology is limited. By our own experience, we build spacecraft using chemical rockets and solar panels. But an advanced civilization might use propulsion systems we can't even conceive of. Any of these scenarios is possible. None can be ruled out, but none can be confirmed either. Not yet. Chapter 17. The comparative ANL-YCS. Let's compare 3I Atlas to the other interstellar objects we've seen. Each one tells us something different about the cosmic neighborhood beyond our solar system. Oumuamua was the first, discovered in October 2017. It was small, maybe 400 meters long, cigar-shaped or possibly flat like a pancake. We're still not sure. It had no visible coma, no tail, nothing that looked like cometary activity. But it accelerated as it moved away from the sun, small but measurable change in velocity that couldn't be explained by gravity alone. Some scientists suggested it was outgassing hydrogen. Others proposed it was made of frozen nitrogen, which would sublimate without leaving visible traces, and Avi Loeb suggested it was a light sailor, thin reflective sheet pushed by solar radiation. The debate continues, but most astronomers lean toward the natural explanation. 2I Borisov was next. Discovered in August 2019, it was clearly a comet-active IC with a coma and a tail. It behaved exactly as comets should. Spectroscopic observations showed water vapor, carbon monoxide, and cyanidal, typical cometary volatiles. The orbit was hyperbolic. The composition was familiar. 2 I Borisov was unremarkable, and that was remarkable because it showed us that comets in other star systems are similar to comets in ours. Now we have 3 Ia Atlas larger than Oumuamua, more active than Borisov, but with anomalies. The acceleration, the nickel, the antitail, the trajectory, alignment. It's neither a simple rock like Oumuamua nor a straightforward comet like Borisov. It's something in between, or something different entirely. And that's what makes it so compelling. It challenges our categories, forces us to expand our understanding, reminds us that the universe is more complex and more surprising than we can imagine. Chapter 18. The observational CMPIGN right now. Telescopes around the world are watching 3IA Atlas, the Keck Observatory in Hawaii, the Very Large Telescope in Chile, the Gemini telescopes, the Hubble Space Telescope, the James Webb Space Telescope. Each one is collecting data photometry, spectroscopy, polarimetry, astrometry. Photometry measures brightness, how the comet's light output changes over time. This can tell us about rotation, outgassing, and structural changes. Spectroscopy breaks light into its component wavelengths, revealing the chemical composition of the coma. Which gases are present, which elements, what ratios. Polarimetry measures the orientation of light waves, telling us about the size and shape of dust particles in the coma. Astrometry measures precise coordinates on the sky. By tracking these over time, we can calculate the orbit with increasing accuracy. All of this data is being fed into models, computer simulations that predict how a comet should behave under different conditions. And those models are being compared to the observations. When there's a mismatch, that's when things get interesting, because a mismatch means our assumptions are wrong, either about the comet's composition or its structure or its behavior. And that's where discoveries happen. The observational campaign will continue through early 2026. By then, we should have a much clearer picture of what 3IA Atlas is and what it's doing. But until then, we're in a state of uncertainty, waiting, wondering. Chapter 19. The mass CLCO, LITO, and LIT return to the question of mass. This is critical to understanding the acceleration. In August, Loeb and his colleagues calculated that 3IA Atlas has a mass of about 33 billion tons. That's based on its brightness, its size estimate, and assumptions about its density. 0.33 billion tons is enormous. It's about 1,000 times more massive than Oumuamua, and significantly more massive than 2I Borisov. If that mass is correct, then producing the observed acceleration through outgassing becomes problematic. You'd need to eject an enormous amount of material, millions of tons, and we don't see evidence of that. But here's the issue. The mass calculation depends on several assumptions. First, the size. We don't have a direct measurement of 3IA Atlas's nucleus. The Hubble observations gave us an upper limit of about 5.6 kilometers in diameter, but the object could be smaller, much smaller. The coma is large, but the nucleus is tiny, and distinguishing between the two at interstellar distances is difficult. Second, the density. We're assuming 3Ia Atlas has a density similar to other comets above 0.5 to 1 gram per cubic centimeter. Porous ice with embedded rock, but what if the density is different? What if the object is more compact or less? If 3Ia Atlas is less dense than we think, the mass goes down and the outgassing explanation becomes more plausible. If it's more dense, the mass goes up, and the outgassing explanation becomes less plausible. We won't know for sure until we get better images, and that brings us back to the high RIC question. Those images, if and when they're released, could resolve the size uncertainty, and that would cascade through all the other calculations: mass, density, outgassing rate, acceleration. Everything hinges on getting that one piece of data. Chapter 20. The CME EINTA RASTE ON October 21st, 2025. The Sun ejected a coronal mass ejection, massive burst of plasma and magnetic field. Billions of tons of charged particles hurled into space at speeds of hundreds of kilometers per second, and 3Ia Atlas was in its path. The CME hit the comet on October 24th, 3 days before perihelion. The timing was notable because CMEs can affect comets, they can trigger outbursts, cause fragmentation, alter the coma structure. Some researchers have suggested that the CME could explain the brightness surge we observed. The intense radiation and charged particles could have heated the nucleus, causing a sudden release of volatiles. That's possible, but the timing is tight. The CME hit on the 24th. The brightness surge was observed from the 21st through the 29th. So the surge started before the CME arrived. Unless the Sun was already ejecting plasma in that direction, earlier CMEs don't happen in isolation. The Sun's activity is complex, with multiple eruptions happening over days or weeks. It's also worth noting that CMEs can impart momentum. Not much, but measurable. If the plasma slammed into 3Ia Atlas asymmetrically, it could have created a small impulse. Could that impulse account for the acceleration? Probably not. The force from ACME is tiny compared to the force required to change the orbit, but it might contribute. It might be part of the explanation, or it might be a red herring, something that looks significant but isn't. Time will tell. Chapter 21. The origin quaestio. In where did 3Ia Atlas come from? We know it came from interstellar space, but which star? System. Astronomers have tried to backtrack the object's trajectory, using its current position and velocity to trace its path backward through the galaxy. They've identified some candidates. One possibility is Barnard's star, a red dwarf, about 6 light-years away, close by galactic standards, and it's moving toward us. In about 10,000 years, it'll be the closest star to our solar system. If 3Ia Atlas was ejected from a planetary system around Barnard's star, the timing could work. The object would have been traveling for tens of thousands of years, maybe hundreds of thousands. Another candidate is a region in the thick disk of the galaxy, an older population of stars located above and below the thin disk where most stars reside. Objects from the thick disk are ancient, formed when the galaxy was younger. If 3Ia Atlas came from there, it could be billions of years old. A relic from an earlier epoch. There's also the possibility that it came from a star we can't identify. dim red dwarf too faint to see, or a dead star. A white dwarf or neutron star whose planetary system was destroyed long ago. We may never know for certain, because the uncertainties in the trajectory grow as we extrapolate backward. Small errors in position or velocity today translate into large errors millions of years ago. But the origin question is important because it tells us something about the distribution of interstellar objects, about how common they are, and about how planetary systems evolve. If 3-Aya Atlas came from a nearby system that suggests interstellar objects are abundant, we should be finding more of them. If it came from the thick disk, that suggests a different story of population of ancient wanderers ejected from systems that formed when the universe was young. Either way, it's a window into the galaxy beyond our solar system, a glimpse of cosmic processes that happened long before we existed. Chapter 22. The SETI EFFO in September 2025. The SETI Institute turned its radio telescopes toward 3-Aya Atlas. SETI stands for Search for Extraterrestrial Intelligence, and for decades, the organization has been listening for signals from space radio, transmissions that might indicate the presence of a technological civilization. They've scanned thousands of stars and found nothing. But 3-Aya Atlas presented a unique opportunity. Object already in our solar system, if it were transmitting, we could detect it. The observations were conducted using the Allen Telescope Array in Californian network of 42 radio dishes, each 6 meters in diameter, working together to scan the sky. They listened at multiple frequencies, the hydrogen line at 1420 megahertz, the water line at 22 gigahertz, and several others that are considered magic frequencies in SETI research. The results? Nothing. No signals, no anomalous emissions, no patterns in the noise. 3-Aya Atlas is radio silent. Now, that doesn't mean it's not technological. A probe might not be transmitting. It might be operating in stealth mode, or it might be using a communication method we can't detect. But the SETI observations do rule out one scenario. If 3-Aya Atlas is a probe, it's not trying to contact us, at least not with radio waves. Chapter 23. The philosophical quasi-UN. Let's step back even further and ask a bigger question. What does it mean if 3-Aya Atlas is artificial? Not in terms of science, not in terms of data, but in terms of humanity or place in the universe. Our understanding of ourselves, for most of human history, we believed we were the center of creation. The Earth was the center of the universe. The sun and stars revolved around us. We were special, chosen. Then Copernicus showed us we were not at the center. The Earth orbits the sun. We're just another planet. Then Galileo showed us the universe is vast. There are other moons, other worlds. We're not unique. Then Darwin showed us we're not separate from nature. We evolved. We're connected to all life on Earth, and now we're confronting the possibility that we're not alone. That intelligence might exist elsewhere, that we're part of a cosmic community. If 3-Aya Atlas is a probe, it changes everything. Not immediately. Not practically, our day-to-day lives would continue. But conceptually, philosophically, it would be a turning point. we would know with certainty that we're not alone, that other minds exist, other civilizations, other ways of being, and that knowledge would reshape how we see ourselves, our priorities, our future. It would also raise uncomfortable questions. Why are they here? What do they want? Are they friendly, hostile, indifferent? And what should we do? Should we try to communicate? Should we prepare defenses? Should we hide? These are not abstract questions. If 3-Aya Atlas is artificial, we need to start thinking about them seriously. But right now, we don't know. And maybe we never will. Because the truth is, the universe doesn't owe us answers. It doesn't care what we believe or what we want. It simply is. And all we can do is observe, measure, calculate, and try to understand. Chapter 24. The next STP. So, where do we go from here? First, we wait for more data. The observations happening now will take weeks to process. The orbital calculations will be refined. The spectroscopic data will be analyzed. We'll get a clearer picture of what 3-Eye Atlas is doing. If the acceleration continues, that's significant. If it stops, that's significant too. Second, we wait for the higher EC images. NASA has said they will be released eventually. When that happens, we'll see the nucleus in unprecedented detail, and that will answer many questions. Third, we wait for the Jupiter flyby. In March 2026, Juno will observe the comet up close. That's our last best chance to learn something definitive. And fourth, we keep watching, because 3-Aya Atlas isn't the last interstellar object we'll ever see. The Vera Rubin Observatory, which came online in 2024, is designed to detect objects like this. It scans the entire sky every few nights, and it's expected to find dozens or even hundreds of interstellar objects over the next decade. Each one will be a data point, a clue, a piece of a larger puzzle. Are interstellar objects common or rare? Are they mostly natural or mostly artificial? We don't know yet. But with each new discovery, we get closer to understanding, and maybe someday we'll find one that's unambiguous, one that's clearly technological, one that answers the question once and for all. Until then, we're left with objects like 3-Aya Atlas, ambiguous, intriguing, frustrating, and fascinating. Chapter 25. The bigger PCTU error. Let's zoom out one more time and consider what this all means for astronomy. For most of history, we studied our own solar system, the planets, the moons, the asteroids. That was the extent of our reach. Then, in the 1990s, we discovered the first exoplanets, planets orbiting other stars. Thousands of them. We learned that planetary systems are common. The planets come in all sizes and configurations. Now, we're starting to study interstellar objects, fragments from other systems passing through ours. And we're learning that space isn't empty. It's full of debris, comets, asteroids, maybe even probes. This is a new frontier, interstellar astronomy, the study of objects that travel between stars. And it's given us a new perspective, because these objects carry information, chemical signatures, structural clues, evidence of the conditions in other systems. 3-Aya Atlas, for example, has a high CO2 content that tells us about the temperature and composition of the disk where it forms. It has nickel but little iron. That tells us about the chemical processes in its birth environment. Even if it's just a comet, it's a valuable Comet messenger from another star. And if it's something more, then it's even more valuable, because it would mean we're not alone. We've been given a gift, a glimpse of someone else's technology, someone else's vision, that's worth studying, worth understanding, worth respecting. Chapter 26. The scientific meter towed throughout this story. We've been following a process, the scientific method. Observe, hypothesize, test, repeat. We observed 3I Atlas. We noticed anomalies. We proposed explanations. And now we're testing those explanations against new data. Some hypotheses will survive. Others will be discarded. That's how science works. But here's the key. Science doesn't demand certainty. It demands honesty. We don't need to know the answer. We just need to follow the evidence. Avi Loeb has been criticized for suggesting 3I Atlas might be artificial. Some scientists say he's being sensational, irresponsible, giving false hope to people who want to believe in aliens. But Loeb would argue he's being honest. The data is ambiguous. The natural explanation has gaps. And until those gaps are filled, we should consider all possibilities. That doesn't mean jumping to conclusions. It means keeping an open mind, and that's what science is supposed to be: open, curious, willing to be wrong. If 3I Atlas turns out to be a comet, Loeb will accept that. He'll move on. He'll apply the same rigorous analysis to the next object. But if it turns out to be something else, then he'll have been vindicated, and science will have advanced. Either way, the process is what matters, not the conclusion. Chapter 27. The human Illuminatials. Not forget the people behind this story. The astronomers who discovered 3IA Atlas, who stayed up late, scanning images, looking for moving objects in a sea of stars. The scientists who analyzed the data, who ran the models, who debated the interpretations, the engineers who built the telescopes, who designed the instruments, who kept them running, and the public of people who follow this story, who ask questions, who care about what's out there. This is a collective effort. Science isn't done in isolation. It's done by communities, teams, networks of people working toward a common goal. And that goal is understanding, not for profit, not for glory, but for the simple joy of knowing what is 3IA Atlas. Where did it come from? What is it doing? We don't know yet, but we're trying to find out. And that effort, that pursuit of knowledge, is what makes us human. Chapter 28. The RAF Lee's CTO, and today is December 19th, 2025, and we're standing at a crossroads. In one direction, 3I Atlas is a comet, unusual, yes, but natural. A product of processes we understand, even if the details are still unclear. In the other direction, it's something more, something we've never seen before. Something that challenges our assumptions about what's possible. We don't know which direction is correct. Not yet. But we know this. The universe is vast, and we've barely scratched the surface. We've explored a tiny fraction of our own solar system. We've detected a tiny fraction of the exoplanets that exist. We've intercepted a tiny fraction of the interstellar objects passing through our neighborhood. There's so much we don't know, so many mysteries waiting to be solved. 3-Aya Atlas is one of those mysteries, maybe the biggest we've encountered. So far, and for now, all we can do is watch and wait and wonder, because the universe doesn't reveal its secrets easily. You have to earn them through patience, through rigor, through humility, and maybe, just maybe, we'll get our answers soon. Or maybe we'll just get more questions. Either way, the journey continues. Epilogue. The WIT the sun rises over Mauna Kea. The KC Observatory domes rotate slowly, tracking objects across the sky. One of them is locked onto a faint point of light in the constellation Vega 3-Ia Atlas. Thousands of kilometers away in Chile, the VLT does the same. And in space, Hubble and JWST turn their eyes toward the Comet data flows. Numbers accumulate, graphs update. Scientists review the results, compare notes, argue, calculate, wonder. Is it accelerating? Yes, is it natural? We think so. Are we sure? No. And so the cycle continues: observation, analysis, debate, uncertainty. This is where we are. This is where we'll stay for now, until the data speaks clearly, until the answer emerges from the noise. Until we know, or until we accept that we might never know, and that, in the end, might be the most important lesson of all. The universe is under no obligation to make sense to us. It doesn't care about our theories or our desires. It simply exists. And we, as observers, as questioners, as seekers of truth, can only do our best to understand it one photon at a time, one measurement at a time, one mystery at a time. 3-Ia Atlas is out there right now, moving through space at 60 kilometers per second, carrying its secrets, holding its answers. And we're down here, watching, waiting, wondering. What are you, 3-Ia Atlas? The question hangs in the air, unanswered. For now, this documentary presents the current state of observations and hypotheses regarding 3-Ia Atlas as of December 19th, 2025. All data referenced is based on published observations and peer-reviewed research. Alternative explanations, including the technological artifact hypothesis, are presented as scientific proposals worthy of investigation, not as established facts. The acceleration is real. The interpretations remain open. Science continues. Chapter 29. The historical CO1 texted, the grand tapestry of human discovery. Few moments have rivaled the potential significance of what we're witnessing with 3-Ia Atlas. To truly grasp the magnitude of this cosmic enigma, we must journey back through time to the very dawn of astronomical observation. When our ancestors first looked up at the night sky and wondered about the points of light that danced across the darkness. For millennia, humanity believed the heavens were immutable, perfect and unchanging. The stars were fixed points on a celestial sphere, and comets were harbingers of doom, divine messages that disrupted the cosmic order. Then, in 1687, Isaac Newton published his Principia Mathematica, revealing that the same laws governing a falling apple also governed the motion of celestial bodies. Suddenly, The universe became knowable, predictable, governed by mathematical laws. Rather than divine whims, this revolutionary understanding birthed the field of celestial mechanics, allowing astronomers to calculate the orbits of planets and comets with astonishing precision. For over 3 centuries, these calculations held true, with objects in space following the paths dictated by gravity and momentum. The cosmos operated like a grand clockwork, and we had finally learned to read its face. Then came 2017, and the arrival of Oumuamua, first confirmed interstellar object to pass through our solar system. It was elongated, tumbling strangely, and, most perplexingly, it accelerated as it left our system, defying the gravitational calculations that should have governed its trajectory. Most scientists attributed this acceleration to outgassing, though no visible coma or tail was detected. A few, including Avi Loeb, dared to suggest an artificial origin. But the scientific consensus leaned toward natural explanations. 2 years later, Tuai Borisov arrived, and it behaved exactly as we expected an interstellar comet to behave with. A visible coma, a tail, and spectroscopic signatures matching our understanding of cometary composition. It was reassuring, a confirmation that our models still worked, that Oumuamua was perhaps an anomaly. Now, with 3IA Atlas, we find ourselves at another crossroads. Like Oumuamua, it exhibits non-gravitational acceleration. But unlike Oumuamua, it shows clear signs of cometary activity, visible coma, brightness changes, spectral signatures of volatiles. Yet these very signs don't fully align with our understanding of cometary behavior. The acceleration is too strong, the composition too unusual, the timing too precise. We're caught between 2 possibilities, each challenging in its own way. Either our understanding of cometary physics is incomplete, requiring us to revise models that have held true for centuries, or we're witnessing something that transcends natural explanation entirely. What makes 3IA Atlas particularly significant is the wealth of observational data we've gathered. With Oumuamua, we had limited time and limited instruments. With 3IA Atlas, we've been watching it for months, with the most advanced telescopes ever built, collecting unprecedented amounts of information. The anomalies we're observing aren't based on sparse data, but on comprehensive measurements that have been verified. This isn't the first time science has faced such a moment. When Uranus was discovered in 1781, its orbit didn't match Newtonian predictions. Astronomers calculated that another planet must be influencing its path, leading to the discovery of Neptune in 1846, a triumph of scientific reasoning. When Mercury's orbit showed similar anomalies, Einstein's general relativity provided the explanation, revolutionizing our understanding of gravity. Perhaps 3IA Atlas represents a similar momenta cosmic puzzle that will force us to expand our understanding, to discover new physical principles, or to acknowledge possibilities we've previously dismissed as science fiction. Chapter 30. The Observational CHL Lian GS. Studying an interstellar object like 3IA Atlas presents unique challenges that push the limits of our observational capabilities. To appreciate the complexity of the task, we must understand the difficulties astronomers face when trying to unravel the mysteries of these cosmic visitors. First, there's the issue of distance. Even at its closest approach, 3IA Atlas remains hundreds of millions of kilometers away. At such distances, even our most powerful telescopes can only resolve the object as a point of light, with the surrounding coma obscuring any details of the nucleus. It's like trying to determine the shape and composition of a snowflake by observing its reflection from a mile away. Then there's the problem of perspective. We're observing 3IA Atlas from a moving platform, or thus, it travels through space. This creates a complex dance of relative motion that must be precisely calculated to determine the object's true trajectory. Small errors in these calculations can compound over time, leading to significant uncertainties in our understanding of its path. The transient nature of interstellar objects adds another layer of difficulty, unlike planets or asteroids that remain. In our solar system, these visitors pass through quickly, giving us only a limited window to observe them. With 3IA Atlas, we've been fortunate to have months of observation time. But even this extended period is insufficient to answer all our questions. The brightness of 3IA Atlas presents its own challenges. As it approaches the Sun, the object becomes more active, developing a coma that can be thousands of kilometers across. This cloud of gas and dust surrounds the nucleus, making it difficult to determine the true size and shape of the object itself. It's like trying to see a person's face while they're standing in a dense fog. SPECTROSCOPIC analysis, while invaluable, comes with limitations. The light from 3IA Atlas must travel through interstellar space, through Earth's atmosphere, and through our instruments before we can analyze it. Each step introduces potential distortions and noise that must be carefully accounted for. The spectral signatures we detect are faint, requiring long exposure times and sophisticated processing techniques to extract meaningful data. Timing is yet another challenge. The most critical moments in 3IA Atlas's journey, its perihelion passage, its closest approaches to planets, its periods of increased activity, happen on their own schedule, not ours. Coordinating observations across multiple telescopes worldwide requires precise planning and sometimes a bit of luck. The Sun itself poses a significant obstacle. When 3IA Atlas passed behind our star, it became invisible to Earth-based telescopes, creating a gap in our observations. During a crucial period, we had to rely on space-based observatories, each with their own limitations and observation schedules. Even the data we collect presents challenges. The sheer volume of information gathered by modern telescopes requires sophisticated algorithms and significant computing power to process. Each observation must be calibrated, corrected for atmospheric and instrumental effects, and interpreted through models that themselves contain assumptions and uncertainties. Despite these challenges, the quality and quantity of data we've gathered on 3IA Atlas represent a significant advancement over what was possible with previous interstellar objects. Each new observation, each carefully analyzed spectrum, each precisely measured position adds another piece to the puzzle, bringing us incrementally closer to understanding this cosmic enigma. Chapter 31. The theoretical Forameter-Woka-2 makes sense of the anomalies presented by 3IA Atlas. We must examine the theoretical frameworks that guide our understanding of cometary, physics, and interstellar objects. These models, built on decades of observation and analysis, provide the foundation against which we measure the unusual behavior we're witnessing. Traditional cometary models are based primarily on our study of solar system comets, particularly short-period comets that originate in the Kuiper belt and long-period comets from the Oort cloud. These models describe comets as dirty snowballs, mixtures of ice, dust, and organic compounds that become active when heated by the sun. As a comet approaches the sun, solar radiation causes volatile ESOs to sublimate directly into gas, creating a coma around the nucleus and forming tails as solar, wind, and radiation pressure push material away. The outgassing creates a non-gravitational force that can alter the comet's orbit. Though this effect is typically small and predictable, the brightness of a comet is expected to increase as it approaches the sun, following a power law relationship that depends on the composition of the volatiles and the distance from our star. Spectroscopic analysis should reveal common cometary molecules like water, carbon dioxide, carbon monoxide, and various organic compounds. For interstellar objects, we've adapted these models, accounting for potentially different compositions based on their formation in other stellar systems. We might expect different ratios of volatiles, unusual dust properties, or novel organic molecules, but the fundamental physics of sublimation and outgassing should remain the same. What makes 3IA Atlas challenging to these models is the combination of factors it presents. The non-gravitational acceleration it exhibits is stronger than what would be expected from typical outgassing, especially given the relatively faint coma we observe. The spectral composition, with its unusual nickel-to-iron ratio, doesn't match our expectations for cometary material. The timing of the acceleration, coinciding with perihelion when the object was hidden from view, raises questions about whether we're missing crucial observations that might explain the phenomenon. The asymmetric brightening concentrated on the sunward side differs from typical cometary behavior, where outgassing usually occurs more uniformly. Some scientists have proposed modifications to existing models to account for these observations. One hypothesis suggests that 3IA Atlas might have a highly heterogeneous composition, with pockets of extremely volatile material that sublimate explosively when exposed to solar heat. Another proposes that the object might have an unusual shape or surface texture that enhances outgassing efficiency. More radical theories suggest that our understanding of radiation pressure might need revision, or that 3IA Atlas could be interacting with the solar wind in unexpected ways. Each of these modifications to our theoretical framework attempts to explain the observations within natural physics, preserving the assumption that we're dealing with a comet, albeit an unusual one. What's remarkable about this scientific moment is how it demonstrates the self-correcting nature of scientific inquiry. When observations don't match predictions, scientists don't discard the data, they revise the models. This process has led to many of our greatest scientific breakthroughs, from the discovery of new elements to the development of quantum mechanics, where the 3IA Atlas ultimately forces a minor revision to cometary physics. or represents something entirely different. The process of questioning, testing, and refining our understanding advances science in ways that will benefit our knowledge of the cosmos, regardless of the final explanation. Chapter 32. The alternative hypothesis. When faced with anomalies that challenge our understanding, science proceeds by considering multiple hypotheses, subjecting each to rigorous testing against the available evidence. With 3IA Atlas, researchers have proposed a range of explanations, from the conventional to the controversial, each attempting to account for the object's unusual behavior. The most straightforward hypothesis is that 3IA Atlas is a natural comet with unusual properties. This explanation maintains that all observed phenomena, including the non-gravitational acceleration, can be explained through known physical processes, even if the specific manifestation is rare. Proponents of this view point out that nature often produces objects that push the boundaries of our expectations, and that interstellar comets might differ significantly from their solar system counterparts. Within this natural framework, several specific mechanisms have been proposed. One suggests that 3IA Atlas might contain a high proportion of supervolatile materials like carbon monoxide or nitrogen, which sublimate at greater distances from the Sun and could produce stronger outgassing effects than water ice. Another proposes that the object might have a highly porous structure, allowing solar radiation to penetrate deeper and trigger more extensive sublimation. A third natural explanation suggests that 3IA Atlas might be experiencing a fragmentation event where large pieces of the nucleus are breaking off and creating asymmetric outgassing patterns. This could explain both the acceleration and the unusual brightening patterns we've observed. Moving beyond conventional cometary explanations, some scientists have proposed that 3IA Atlas might represent a new class of objects that we haven't encountered before. Perhaps it's a fragment of a dwarf planet from another stellar system, with composition and properties that differ significantly from solar system objects. Or it might be an aggregate of different materials that came together in the interstellar medium, creating a hybrid object with unique characteristics. More controversial hypotheses venture into the realm of extraterrestrial technology. Avi Loeb and his colleagues have carefully proposed that 3IA Atlas might be a technological artifact of some kind, a probe, a relay station, or even a piece of equipment designed to study solar systems. This explanation would account for the object's acceleration as deliberate maneuvering rather than natural outgassing. Within this technological framework, several specific possibilities have been suggested. One proposes that 3IA Atlas might be a solar sail using radiation pressure for propulsion. Another suggests it could be a light sail probe, similar to concepts being developed for interstellar travel within our own civilization. A third possibility is that it might be a self-replicating probe designed to explore multiple star systems. Even more speculative hypotheses suggest that 3IA Atlas might be a beacon or marker left by an advanced civilization to indicate their presence, or to serve as a navigation aid. Some have even proposed that it could be a weapon or defensive system, though this explanation lacks supporting evidence and ventures into the realm of speculation without observational bases. What's important to understand is that these hypotheses aren't equally supported by the evidence. The scientific method requires that we prefer explanations that require the fewest assumptions and that best account for all available observations. Currently, the natural comet explanation, while requiring some unusual properties, remains the most parsimonious explanation for three-eye atlas's behavior. However, science advances by keeping an open mind to all possibilities, especially when faced with genuinely anomalous data. The history of astronomy is filled with examples of phenomena that were initially dismissed as impossible, but later proved to be real. From pulsars to exoplanets to gravitational waves. What makes Three-Eye Atlas particularly intriguing is that multiple independent observations point to anomalies that don't fit neatly into our existing frameworks. Whether these anomalies ultimately have a natural explanation or represent something extraordinary, the process of carefully evaluating all hypotheses strengthens our understanding and prepares us for whatever discoveries the future may hold. Chapter 33. The cultural IEMPA's CMP see beyond the scientific questions raised by Three-Eye Atlas. Its discovery has had a profound cultural impact, reflecting our enduring fascination with the possibility of extraterrestrial life and our place in the cosmos. This cosmic visitor has captured the public imagination in ways that few astronomical discoveries have, becoming a focal point for our hopes, fears, and wonder about the universe. In the weeks following the announcement of Three-Eye Atlas's unusual acceleration, social media platforms exploded with speculation, theories, and artistic interpretations. Hashtags related to the object trended globally as people from diverse backgrounds engaged in discussions about its nature and significance. Memes comparing Three-Eye Atlas to various science fiction references proliferated, while serious debates about the implications of potential extraterrestrial technology unfolded, alongside more light-hearted commentary that traditional media outlets covered the story extensively, with newspapers, magazines, and television programs dedicating significant coverage to the developing scientific narrative. Documentaries were rushed into production, exploring the history of interstellar objects and the possibility of extraterrestrial intelligence. Podcasts featured interviews with astronomers, physicists, and even philosophers discussing the broader implications of the discovery. The art world responded with creative interpretations of Three-Eye Atlas and what it might represent. Painters, sculptors, and digital artists created works inspired by the object's mysterious nature, while musicians composed pieces that captured the sense of wonder and uncertainty surrounding its visit. Writers of fiction and poetry found in Three-Eye Atlas a powerful symbol for humanity's cosmic loneliness and our search for connection in the vastness of space. Perhaps most significantly, Three-Eye Atlas has prompted renewed public interest in your and humanity, writers of fiction, and humanity, writers of fiction, and poetry found in Three-Eye Atlas, a powerful symbol for humanity's cosmic loneliness and our search for connection in the vastness of space. Perhaps most significantly, in most side C, for where swas CII, Iako, the Sabe Psi, hate, the best Cas, gain, in your astronomy and space exploration. Planetariums and observatories reported increased attendance, with people eager to learn more about this cosmic visitor and the science being used to study it. Amateur astronomers pointed their telescopes toward the constellation where 3IA Atlas was visible, sharing their observations and contributing to the collective effort to understand the phenomenon. The object has also sparked philosophical and theological discussions about humanity's place in the universe. Religious leaders and thinkers have grappled with the potential implications of discovering extraterrestrial technology. Considering how such a revelation might intersect with various belief systems, ethicists have debated how humanity should respond if 3IA Atlas were confirmed to be of artificial origin, raising questions about communication, interaction, and potential risks. This cultural impact reflects something fundamental about the human psyche, our enduring need to understand our relationship to the cosmos and whether we are alone in the universe. 3IA Atlas has become a mirror for our hopes and fears, a canvas onto which we project our speculations about what might exist beyond the boundaries of our world. What's particularly noteworthy about this cultural response is how it differs from previous astronomical discoveries. When exoplanets were first discovered, there was excitement, but it remained largely within scientific circles. When gravitational waves were detected, there was celebration among physicists, but limited public engagement. 3IA Atlas, by contrast, has captured the public imagination in a way that suggests something deeper is at play. Perhaps this is because the possibility of extraterrestrial technology touches on questions that have fascinated humanity for millennia. Are we alone? Is there intelligent life elsewhere? What would contact mean for our civilization? These questions have inspired countless works of fiction, philosophical treatises, and even religious movements, but they have remained in the realm of speculation until now, whether 3IA Atlas ultimately proves to be natural or artificial. Its cultural impact has already demonstrated something important about our relationship to the cosmos. We are a species that looks to the stars with wonder, that seeks understanding beyond the boundaries of our world, that finds meaning in the search for answers to our most fundamental questions. In this sense, 3IA Atlas has already given us something valuable, regardless of its ultimate nature, moment of global unity in wonder, a shared experience of cosmic mystery that transcends cultural, national, and ideological boundaries. In a world often divided by differences, this cosmic visitor has reminded us of our common humanity and our shared place in the universe. Chapter 34. The Future of Interstellar STUDIS. The ultimate explanation for 3IA Atlas, its discovery, has already transformed the field of interstellar studies, creating new opportunities for research and collaboration that will benefit astronomy for decades to come. The scientific infrastructure developed to study this object represents a significant advancement in our ability to detect, track, and analyze cosmic visitors from beyond our solar system. One of the most important developments has been the creation of coordinated observation networks that allow telescopes around the world to work together seamlessly. When 3IA Atlas was first identified as potentially unusual, astronomers rapidly organized a global response, with observatories in different time zones handing off observation schedules as Earth rotated. This collaborative approach ensured continuous monitoring of the object, maximizing the scientific return from each observation window. The data processing pipelines developed to handle the influx of information from these observations represent another significant advancement. Modern telescopes generate enormous amounts of data, and the specialized algorithms created to analyze 3-Aya atlases' spectral signatures, brightness variations, and positional changes have already been adapted for other astronomical applications. These tools will continue to benefit the broader scientific community long after 3-Aya Atlas has left our solar system. The theoretical work prompted by 3-Aya Atlas's anomalies has also advanced our understanding of cometary physics and interstellar objects. The models developed to explain its unusual behavior, whether natural or artificial, have expanded our conceptual framework for thinking about objects that travel between stars. These theoretical advances will inform our approach to future discoveries, helping us recognize patterns and anomalies that might otherwise be missed. Perhaps most importantly, 3-Aya Atlas has demonstrated the value of rapid response in astronomical research. The object's passage through our solar system was relatively brief, requiring scientists to mobilize quickly to make the most of the observation window. This experience has highlighted the need for flexible funding mechanisms and streamlined approval processes that can accelerate research when unexpected discoveries occur. Looking to the future, several new observatories and missions will enhance our ability to study interstellar objects. The Vera Rubin Observatory, already operational in Chile, is conducting a comprehensive survey of the sky that is expected to detect dozens or even hundreds of interstellar objects over the next decade. Each new discovery will add to our understanding of these cosmic visitors, and their diversity. Space-based observatories will also play an increasingly important role. The James Webb Space Telescope, with its powerful infrared capabilities, can detect heat signatures that might reveal the true size and composition of interstellar objects, even when they're surrounded by bright comas. Future missions, specifically designed to study interstellar objects, are already being discussed, with proposals for spacecraft that could rendezvous with the next visitor that passes through our solar system. International collaboration will be essential for these future efforts. The study of 3-Aya Atlas has already demonstrated the value of global cooperation in astronomy, with researchers from around the world sharing data, resources, and expertise. This collaborative model will become increasingly important as we develop more ambitious plans for studying interstellar objects. The technological applications of this research extend beyond pure astronomy. The techniques developed to track and analyze 3-Aya Atlas could have practical applications for planetary defense, helping us identify and characterize potentially hazardous objects that might threaten Earth. The propulsion concepts considered in explaining the object's acceleration might inspire new technologies for space exploration within our own solar system. Education and public outreach represent another important dimension of the future of interstellar studies. The public fascination with 3-Aya Atlas has created an opportunity to engage people with science and to inspire the next generation of astronomers, physicists, and engineers. Educational programs developed around this discovery will continue to benefit students and enthusiasts for years to come. As we look to the future, it's worth remembering that each new discovery builds on the foundation of previous work. The study of 3IA Atlas stands on the shoulders of centuries of astronomical research, from Galileo's first telescopic observations to the sophisticated instruments we use today. Similarly, the knowledge gained from studying this cosmic visitor will inform and inspire future discoveries that we can barely imagine today. Chapter 35. The methodological APPR-ASA to truly appreciate the scientific significance of 3I Atlas. We must understand the rigorous methodologies employed in its study. The investigation of this interstellar visitor represents a in astronomical research, demonstrating how modern science approaches phenomena that challenge our understanding of the cosmos. The process began with detection. Using automated survey telescopes that continuously scan the sky for moving objects. These systems employ sophisticated algorithms to distinguish between asteroids, comets, and other celestial bodies, flagging anything that follows an unusual trajectory. When 3IA Atlas was first identified, its hyperbolic orbit immediately marked it as potentially interstellar, triggering an elevated level of scientific interest. Once identified as an interstellar object, 3IA Atlas became the subject of intensive observation across multiple wavelengths. Different telescopes and instruments were deployed to gather various types of data, each providing unique insights into the object's properties. Optical telescopes tracked its position and brightness. Radio observatories searched for any artificial signals, and spectrographs analyzed the composition of its coma. The positional data, or astrometry, was particularly crucial. By measuring 3IA Atlas's location relative to background stars with extreme precision, astronomers could calculate its trajectory with increasing accuracy. This positional tracking revealed the non-gravitational acceleration that made the object so intriguing, as its path deviated from what gravitational calculations alone would predict. Photometric observations measuring the object's brightness over time revealed patterns of variability that suggested rotation and potential outgassing events. These brightness changes were carefully analyzed to distinguish between rotational effects and actual changes in the object's luminosity due to cometary activity. Spectroscopic analysis provided perhaps the most detailed information about 3IA Atlas's composition. By spreading the object's light into its component wavelengths, astronomers could identify specific elements and molecules present in its coma. The unusual nickel-to-iron ratio that emerged from this analysis became one of the key anomalies challenging conventional explanations. Polarimetric measurements added another dimension to the investigation. By analyzing how light from 3IA Atlas was polarized as it passed through the coma, scientists could infer properties of the dust particles, including their size, distribution, and composition. These measurements helped constrain models of the object's structure and activity. Each type of observation required careful calibration to account for instrumental effects, atmospheric distortions, and other potential sources of error. The raw data underwent extensive processing before it could be used for scientific analysis, with multiple independent teams verifying results to ensure their reliability. The theoretical modeling component of the investigation was equally rigorous. Scientists developed computer simulations to test various hypotheses about 3IA Atlas's behavior, from conventional cometary outgassing to more exotic explanations. These models incorporated complex physics, including thermodynamics, radiation, pressure, and gravitational interactions. Peer review played a crucial role throughout the process. Research papers about 3IA Atlas underwent rigorous evaluation by independent experts before publication, ensuring the claims were properly supported by evidence and that alternative explanations were adequately considered. This process helps maintain scientific standards, even when dealing with potentially extraordinary discoveries. The methodology also emphasized transparency and reproducibility. Data from observations was made available to the broader scientific community, allowing independent researchers to verify results and conduct their own analyses. This open approach accelerates scientific progress and helps guard against bias or error. Perhaps most importantly, the methodological approach to 3I Atlas maintained a careful balance between openness to new possibilities and adherence to scientific standards, while researchers considered unconventional explanations, including the possibility of artificial origin. They did so within a framework that demanded evidence and logical consistency. This methodological rigor is what gives confidence to the scientific conclusions drawn about 3IA Atlas, even as uncertainties remain. It demonstrates how science can approach genuinely mysterious phenomena without abandoning its commitment to evidence-based reasoning, maintaining intellectual humility while still pursuing bold hypotheses. The study of 3IA Atlas also illustrates the interdisciplinary nature of modern astronomy. Understanding this object required expertise from diverse fields, including physics, chemistry, computer science, and even philosophy. This collaborative approach, bringing together different perspectives and specialized knowledge, enriched the investigation and led to insights that might have been missed within a single discipline. As we continue to analyze the data gathered from 3IA Atlas and prepare for future discoveries, the methodological framework developed during this investigation will serve as a model for how science can approach cosmic mysteries that challenge our understanding of the universe. Chapter 36. The Cosmic PSI VI in our focused examination of 3IA Atlas and its peculiar behaviors. It's easy to lose sight of the broader cosmic context in which this discovery unfolds. To truly appreciate the significance of this interstellar visitor, we must zoom out both in space and time. Consider our place in the vast tapestry of the cosmos. Our Milky Way galaxy contains between 100 and 400 billion stars, each potentially hosting planets, asteroids, and comets of their own. Beyond our galaxy lies the observable universe, containing an estimated 2 trillion galaxies, each with billions or trillions of stars. The numbers are mind-boggling, far beyond human comprehension, yet they represent the true scale of the cosmic neighborhood in which 3IA Atlas has been traveling. In this immense cosmic ocean, interstellar objects like 3IA Atlas are the driftwood, carrying information from distant shores to our own. Each such object is a messenger, having traveled for potentially millions of years through the void between stars, preserving a record of the conditions in its place of origin. When we study 3IA Atlas, we're not just examining a curious object, we're sampling another part of the galaxy, gaining insights into stellar systems we may never directly observe. The journey of 3IA Atlas through our solar system represents just a tiny fraction of its existence. Before reaching us, it likely spent millions or billions of years in the interstellar medium, exposed to cosmic radiation, gravitational influences, and collisions with dust particles. Each of these processes left its mark, creating a complex history that we're only beginning to decipher. What's particularly remarkable is that 3IA Atlas has survived this journey at all. The interstellar medium is not empty. It contains gas, dust, and radiation that can gradually erode or destroy objects over time. The fact that 3IA Atlas remains intact enough to exhibit the behaviors we observe suggests it's either relatively young, unusually robust, or perhaps even actively maintained. The timing of its passage through our solar system is another fascinating aspect to consider. In the 4.5 billion year history of our solar system, 3IA Atlas is only the third confirmed interstellar object we've detected. This suggests either that such objects are rare, that they're difficult to detect, or that we've only recently developed the capability to identify them. The truth is likely a combination of all three factors. From a cosmic perspective, the human timeline for observing 3IA Atlas is vanishingly brief. We've been watching this object for months, but it has been traveling through space for eons. Our observations represent a mere snapshot in its long existence, like a single frame in an epic film that spans millions of years. This temporal disparity highlights the limitations of our understanding. We're trying to reconstruct the complete story of 3IA Atlas from a brief glimpse, like paleontologists attempting to recreate an entire dinosaur from a single bone. The conclusions we draw must necessarily be provisional, subject to revision as more data becomes available. The cosmic perspective also reminds us of our technological limitations. As advanced as our instruments may seem, they're still crude tools for studying the subtleties of interstellar objects. Future generations will likely look back on our efforts with the same mixture of admiration and amusement with which we view the new astronomical instruments of centuries past. Perhaps most importantly, the cosmic perspective contextualizes our search for extraterrestrial intelligence. If technological civilizations exist elsewhere in the galaxy, they would have had billions of years to develop and spread. The absence of obvious evidence for such civilizations, the Fermi paradox, becomes even more puzzling when we consider the vast timescales and distances involved. In this context, the possibility that 3IA Atlas might be artificial takes on profound significance. It would suggest that we're not alone in the cosmos, that other minds have looked up at their own skies and wondered about the universe, just as we do. It would represent the beginning of a new chapter in human history, transforming our understanding of our place in the cosmos.